Hello, I'm MC Toon, and it is Tuesday night. Tonight we've got a debate with Fung, who goes by Globby's Hay. Don't know what that means, but that's his name on Facebook, Globby's Hay, Hey. I've sent him the link. He's said okay. He's not quite here yet, so I'll cover a few things while we wait. In the chat, people have been talking about cations. In fact, you may remember from last week when we found out that sodium is the major cation. Probably the funniest misunderstanding ever. If you've missed that, you could go and you can look for the Simpsons Cletus icon, a thumbnail, and watch that video. It's a short section of it, or watch the whole thing with Trey Hutchinson. It's fantastic. He claims to be a mechanical engineer, but doesn't know anything about anything that an engineer would definitely know about. And before it started, I did get a super chat from Andreas Eld. I'll read that quick. Says, science is obviously conspiracy. Why else is the speed of sound 666 half meters per second? Hail Sagan. Yes. You can invent numbers arbitrarily, doing math on them for no good reason, just to get your a couple sixes out of it if you want. So, well, so what is going on, Fung? I know he's used Zoom before because he's been on with FTFE before. So, and he uses Zoom. So I don't know. We'll have to see what's going on. I specifically asked Fung to cover one thing that he covered with FTFE, which was what he called the Black Swan. We'll see what that is, what he's talking about, how this does it. He says he just woke up. He knew about this time. Just woke up. It's 10 a.m. in Hong Kong right now, where he's at. So maybe he's got to get himself prettied up. He says, "Give me a few minutes." Yep. So you know, I sent him a message a while ago, and he responded that he's okay with it. So what do you know? Flurf not ready. So I need to open up my tab here. So anyway, let's see. We got Perp for 2 Australians says, "What is your major cation, sir?" Major malcation. What is major malcation, sir? Oh, that's awesome. The Flurf, they run on Flurf time. They do run on Flurf time, which is whatever time they show up. There's a process to keeping them showing up. And it's tough. It takes effort. And I figured out over a couple hundred debates kind of how to do it. I tend to poke them off, and I'll send them a note the 2 days before, day before, day of, just to keep it fresh in their mind, because, you know, a lot of these people, they don't have a whole lot of responsibilities. So they're a little lost sometimes. So it helps to do that. I did ask Fung if he likes an avatar. If you notice, there isn't really an avatar for this video. He didn't have one. That's why. So if they don't want an avatar, I just put up some derpy flat earth picture. Alyssum says we should ask him for his education. Cajun with a J. Oh, it's awesome. Being on time and responsible is hard. They don't know how to adult. Yes, that is one of the problems, I guess, with them. I don't know if you are on Facebook. This last couple days, they have come out in droves of craziness. really aggressively crazier than ever. Like the memes that they've put up are the dumbest ones. It's like they're in a competition to have the absolute stupidest possible meme or the biggest misunderstanding of physics out there. It's and it's like a 700-way tie for first on who doesn't understand these things. Um, it's nonstop idiocy from them, and yet they all think that they're smarter than all of the scientists of the world somehow. These poor guys, that they're not. It's really, how do you live your life being really dumb? I just gotta be honest. They're not smart, but they think they are the most geniuses ever to grace the face of the flat Earth, according to them. And they'll say stupid things like, the second law of thermodynamics requires a physical container. Like, so you ask them, well, where's that citation? Can you just, quote me the part of the second law of thermodynamics, or maybe from a textbook on thermodynamics, show where it talks about pressure in a physical container? Nothing. They don't have it. They'll go and they'll cite, I was just today on Twitter, they'll cite a section of a article on thermodynamics, but it doesn't say what they think it says. And then I say to them, I said, tell you what, how about you contact the author and see if he agrees with you? No, they would never do that, because they know the author won't agree with them. You can't. They can only cherry pick. So, do I have Venmo or PayPal? Says Fox Populi. I have no, I have Cash App. And I think I'm just MC Toon on Cash App. I do have Patreon. They do a pretty good job. I haven't set up my PayPal yet. I did it, but I have to do it like as a business, so I can't. It's not done yet, so I need to send some. They want it on some official letterhead. So it means I have to invent some official letterhead. None of them could disprove flat Earth. That's how they know they're smart. Yeah, exactly. Oh, and Golden Knight, I like this. You and FTFE should show favorite Flurf memes whenever Flurf doesn't show for a debate. Yeah, that's... I have stuff typically ready. I have a folder of things for when they don't show. But Fung has said he's going to show, so anyway. Let me see. All right. There it is. What is, my Cash App is $MCTOON. But that's not, you don't have to do that. I just thought do whatever you want. I do this for fun. I love doing it. Getting paid makes it worth a bit more of the effort that I put in. So he's gonna show up. Is that Nerial? I think that's Nerial. Fung is ready to go almost. He just woke up. He's in Hong Kong, so his time zone is 10 a.m. And you may wonder, why am I early? I'm a little earlier than usual. I had messed up on daylight savings. I looked at the time last week just for a 8 p.m. Versus Hong Kong, and I didn't do it for the specific day. This last weekend was daylight savings, so it shifted by an hour. I know, don't change things last minute on a Flurf, so I didn't want to do it last night. Maybe I should have tried. Give him another hour to sleep. There's Citizen 9 says there's definitely some stiff competition going on at the moment. Raichi versus Mitch versus Flatzoid. Although Flatzoid has gone full religitard now for some reason. Really? Flatzoid's a religious Flurf. I didn't I didn't know that. Get my tune shine going here just a second. Um, oh, this weekend, Saturday. Saturday, I am in a debate, a modern day debate on the moon landing with Alex, who is Alex Stein, Conspiracy Castle. But guess what? We have Fung in the house. Fung, can you hear me?
Hello?
Hello. People can hear you, Fung.
Am I coming through okay?
I think so. People, how does Fung sound to you? Got my tune shine going here.
Oops.
Mm-mm. Stringer News 1 says, if there's daylight savings time, when is daylight wastings time? I do not like daylight savings time. I would get rid of it if I could. NANA says, oh my gosh, I gotta back up a little bit. P Barnes says, this meme has all the indications of being as big as Dr. Peel. I hope so. It's so funny. NANA for $6.66 says, memes are inherently dumb. Hail Santa. Yes, memes are. Rev Elation says, spells out flat Earth on the phone numbers, which is 3528-32784 equals 42, or 6 plus 6 plus 6 plus 6 plus 6 plus 6. Cannot deny that. Can you, Fung? Undeniable. Fung, I got a question for you from Indie Tiger. Is your last name Gus?
No. Why?
That would make your name Fungus.
No, 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 no. That is not.
Can you can you explain your name on Facebook? Why is it Globby's Hay?
Well, I don't want to use my real name, so I make up a fake name. So I created the account solely to discuss the shape of the Earth. So I will, I guess, maybe I'll just go with the name Globy, and then turns out that Globy is not allowed for a name in Facebook. So the next thing closest to Globy is Globby. So
Okay.
there it is.
And why Hay? Hey?
Well, you have to put in something. So yeah, honestly, I didn't put in much thought into that. So
All right, that sounds about right. Okay, well, welcome, Fung. We kind of already discussed the topic here, but if you wanna just say a little bit about yourself before we go.
yeah, my name is Fung, and I live in Hong Kong. I just woke up in the morning. It's 9:15 for me, so I'm basically just trying to clear up my mind, and happy to be here.
Right. So, do you wanna get going? Get started. Um, you tell you what,
Yeah.
because you're not on screen. What I'll do is I will try to keep up by whatever you're going over by presenting on
Oh,
screen, so that people can see what you're talking about. Is that
okay.
so? If I ask you to like cover something or kind of fill in the gaps, it's just so that I can have it um, uh, keeping up. I'm not trying to interrupt or anything. That sound good?
Yeah, yeah, sure, sure, sure.
All right.
Uh, I I would like to share my PowerPoint, please.
Oh, sure. Let's see. Is it on? And there you go. It'll let you share now.
Okay, sure. I say share my PowerPoint, but I don't use that often, so. uh, is my screen on?
Oh yeah. Hold on a second. It's
Okay.
It's gone full screen for me, which I don't want.
Oh, that's very nice.
There we go. Okay.
Right. So the topic is the shape of the Earth, obviously. In the chat, you mentioned a flat Earth proof. It's called a black bird. It's actually called a black swan. So this is it.
Okay.
Would you like to talk about it?
Yeah, go ahead.
Okay. So the argument is about the horizon. You see, if we are living in a globe of 59 miles in radius, there is a certain physical constraints in the geometry of the globe Earth. So the map says if the Earth is a sphere of 59 miles, so then every horizon distance can be no more than 1.22 times the square root of height in feet.
And where's that from?
Actually, it's from the Globe Earth calculator, and it's backed up by a subject matter expert, Andrew Thomas Young, is an astronomy professor.
Can we look at his citation for that? Do you have that?
I have it somewhere. Hold on. Oh yeah, this one. It's the photo
like,
part.
like, is it in a book or is it on a website or is it in a paper or something? Can you send the link to wherever he published it?
It's on a website. It's on the website. So
can you send that website so we can look at it?
Well, I can't do it now because I only got his quote here written down.
Could I look it up quick while you're?
Mike, can I call you Mike?
Sure.
Yeah, but Mike, this is actually basic geometry of the globe Earth. It's not something that flat earthers make up. So
yeah, I just want to look at the publication.
This is the math. So
I want to look at it. That I want to see the derivation of it. Can you send that, please? Oh, I'll wait. You can take your time and find it.
This is the map. So
that's not the where is 1.23? What's that number? Where did that number come from?
It's the globe Earth curve calculator, because you see,
I've never seen 1.23 in a globe Earth calculator. So that's why I'm asking for the derivation of that number. Where did the 1.23 come from? Was it just a number that was pulled out of the air? Is it because that's not the radius of the Earth. It's not 1.23. That's not the radius of the Earth, right? Well, so
it's the distance. It's the distance to the horizon.
Yeah, you said that, but I want to see the derivation of the formula, please.
Well, unfortunately, I don't have it right here. So you're either
okay. Well, then let's find it right now. Where did he publish this? You certainly didn't just invent this. You got it from somewhere. So let's find where it's from. So Andrew Thomas Young, San Diego State University. So if I search for Andrew Young, and then what is this? This is the distance to the horizon. Let me do that. Yeah. Andrew Young, distance to the horizon. All right. And let's see. The first link here. I have it. I think I have right now. I have the look. You mind if I share my screen to you and you tell me if?
Yeah, I think we've got the same one. If agents. Yeah, sure. See if this.
All right.
Shouldn't be hard to find it.
All right. Do you see that right there?
Yeah.
Is that what you're talking about? This is Andrew T. Young, right? Is that it?
Yep.
And then the distance to the horizon. Okay, so good. This is the derivation. Let's just go over this quick. So can you want to cover this quick?
Yeah.
All right, go ahead. Do,
Well,
do you want to just cover how he got the number?
yeah, you can just you can basically read out the bottom part
Oh,
numerically.
all
The
right.
radius
I'll read it then. All right.
varies a little with
Um,
altitude direction.
Here, I'll read it. Without refraction, the matter is very simple. Here's the diagram from my dip page, and that's his diagram here. It shows a vertical plane through the center of the Earth at C, and the observer at O. The radius of the Earth is R, and the observer's height is h above point S on the surface. Of course, the height of the eye and consequently the distance to the horizon is greatly exaggerated in this diagram. It's not to scale here. The observer's astronomical horizon is the dashed line through O. So it starts at the top and goes diagonally down there. Perpendicular to the Earth's radius OC. Oh no, that's the top one, is the astronomical horizon. But the observer's apparent horizon is dashed line OG. That's the diagonal one. Tangent to the surface of the Earth. Point G is the geometric horizon.
Yeah.
There we go. Elementary geometry tells us that because the angle between dash line G is at a right angle, the distance OG from any observer to the horizon is related to the radius and the observer's height by the Pythagorean theorem, given right there, or, and then he solves for OG, but if we expand terms there, things cancel, and he says we have OG equals square root 2 times radius times the height plus the height squared. Then he says it's customary to use the fact that the height is significantly smaller than the radius at this point, so we could neglect the second term. Then OG equals square root of 2 times the radius of the Earth times h. Is the distance to the horizon neglecting refraction? He has neglecting refraction in bold here. Numerically, the radius of the Earth varies a little with latitude and direction, but a typical value of 6,378 kilometers, or about 3,963 miles. If h is in meters, that makes the distance to the geometric horizon 3.57 kilometers times the square root of the eye height in meters, or about 1.23, and that's where I think you got it from, right? Times the square root of the eye height in feet.
Yeah, that's basically
right?
my quote.
So okay, so let's do that. I want to make sure I have this down really well here, because it's to the people at home, it might be a little unfamiliar. So what I'll do is I will send this. All right. So the people at home see the same thing as you do there. So we have the distance is the square root of 2 times the radius of the Earth times the height of the observer.
Okay.
Right? But he got 1.22 out of it somehow, right?
Yeah.
So I think what he did because he said this is in feet, h is in feet, but the radius we use typically miles, and he used a specific number for miles. So 2 times, and he used let's see if I can remember, 3,963 miles, right? But he divided by, he had to get to get the miles out of there, he had to divide by the feet per mile, right? How many feet per mile?
Basically, what it boils down to is,
wait, I'm not done with the derivation. What's the number of feet per mile? Do you remember?
I don't.
Okay, it's 5280. Right? So that's going to give us, let's see here. We got 2, 3,963 63, 5280 divide times. Okay, so we've got the square root 1.5011 times h, right? But now we can get the 1.5011 out, right? What do we do?
I'm not very good at math, so go
Oh.
ahead and make your...
Well, we just take the square root of 1.5011, giving us d equals 1.225 root h, which needs to be in feet. Okay, so that's where it came from, right? I just want to make sure for the people at following along at home where this came from, and that's specifically said a couple times, neglecting refraction, right?
Yes, it
Okay.
does.
All right. So,
okay, so
I think we're good
it boils down to is if the observer height is in 1 foot, the geometric horizon can be no more than 1.2, 1.23. Here you say 1.225.
neglecting refraction.
Times the square root of the eye height in feet. Since the eye observer height is 1 foot, so that makes it 1. So the geometric horizon distance from 1 foot observer height will be at 1.23 miles out, without the refraction he's referring to. So, and this is the black swan photo. The observer height is 1 foot. And then you see the two platforms.
Do you want to share your screen again?
Am I not sharing my screen?
No, when I shared my screen to you, it yeah.
Okay. Yep.
All right, got it.
Okay. So this is the black swan picture. You see platform hill house and platform habitat. They are situated in 6.2 miles and 9.4 miles respectively. And the horizon you can clearly see is beyond platform habitat, which is beyond 9.4 miles. So the horizon appears in a distance that is impossible for a globe Earth.
Neglecting refraction.
Yeah. Yes, and then yes, this is the black swan photo. I'm sure if anyone has spent any time on the subject would come across this picture.
So I see on the left side there that there's a crane way off on the left side, and it's all crooked.
Yes, it is.
Why is it all so horribly crooked?
Well, two things here. The crane appears to be bendy. It is obviously because of refraction. We all know that refraction exists. But my argument is about the horizon. As I stated before, for a Earth to be a sphere, there is a certain geometric limitation to the horizon.
Neglecting refraction, of course.
That is the sphere edge of the ball of the globe, right? So the mathematics says is ought to be in 1.22 miles, 1.22 mile out, but the reality is I can safely say is beyond 10 miles.
Sure, but neglecting refraction, of course,
as shown on the picture.
Yep. So refraction. Okay, so can you do, because I see on the page here from Andrew Young, what did you call him? Subject matter.
Yeah, subject matter expert.
Okay, so now he continues on. He continues on to talk about how to do the analysis with refraction. So could you provide that analysis, please?
Yes, and then he later on goes to say that of course there is refraction, but refraction by refraction, what he means is standard refraction or terrestrial refraction. It's basically 7/6 of the radius of the Earth. So what he's saying that is light always bends following the curve of the curvature of the Earth. So the light bands travel in a band
Sure.
fashion.
Yep.
Yeah.
Yeah. So
But
can you
yeah.
do you have in your slide here a slide applying the refraction that Andrew Thomas Young, subject matter expert, talked about? Did you do that analysis?
You mean how do we get the 7/6R?
No. I'm not talking about. Clearly, this isn't 7/6R refraction. This is significantly outside of 7/6R refraction. So could you present your analysis of the refraction of this particular observation?
Well,
Go,
we,
go ahead.
yeah,
Yeah. Do you
refraction.
have that slide? Do you have like a slide that works through the different major effects due to refraction? Because simple refraction, 7/6R refraction, doesn't cause the crane to get all bendy like that. It would cause the crane to be slightly compressed. Not much at all. You might not even notice, because the compression of 7/6R would be very, very slight and very consistent too. Clearly, this is neither 7/6 small and not consistent. So where's the... And just go to your slide that has the analysis of the refraction.
Do I have to? Sorry, do I have it? The refraction. This one. Is this the atmospheric refraction you're referring to? Basically, there are 5 main effects of the atmospheric refraction. There are mirages where the images appears to be upside down, and then there is a looming, towering, stooping, and sinking. I think what happens to the crane is stooping. Yeah,
Well,
I think it's stooping.
I think there's a lot of things happening to the crane all simultaneously. Not
But
just one thing.
sorry,
Lot of things. Yeah.
but my argument is not about the crane. The crane is over here for
Absolutely, yeah. So
but-
where's the analysis based on subject matter expert Andrew Thomas Young's website, where he talks about refraction? Where's your analysis of the refraction that's happening here?
He didn't mention anything about atmospheric refraction. He only specifies terrestrial or standard refraction.
Tell you what, I'll share the page back to you again so you can see where he talks about it. Okay. So here we go.
But my argument is not about the crane. You see?
No, I'm not. No, I completely agree. So let's go over the refraction part of it. This is considered simply, right? Which clearly is not the case. But we'll work into it. I think he must get into a more complicated analysis. So let's try to allow for refraction. Usually air density at the surface, so the rays of light are concave toward the surface. See the bending page for details. The solid arc OH now represents the curved line of sight H. See how it's curved there. H is the refracted apparent horizon. Notice the refraction lets us see a little farther if the ray is concave towards the Earth, as shown here. If we can assume a constant lapse rate, which clearly we cannot, because if it was a constant lapse rate, then the crane would not be all bendy like that. It would be constant. But again, this is the simple version of it. The air between the eye and the Earth's surface and the observer's height is small compared to the 8-kilometer height of the homogeneous atmosphere. Then we can assume the curved ray is an arc of a circle. This assumption makes things easy because the relative curvature of the ray and the Earth's surface is all that matters. In effect, we can use a previous result, but just use an effective radius of curvature for the Earth that's bigger than the real one. Right? This assumption is made so often, it's conventional in surveying and geodesy to use a refraction constant. That's just the ratio of two curves. A typical value of the ratio is about 1/7. Now, I think that you're talking about this 7/6. I think they're adding 1/7. I see where he's going here. He's using that as the coefficient of refraction.
Yeah, that's
Yeah,
the
and you can see here,
standard
yeah,
refraction.
yeah, right there, 6/7r, right? So your r prime is r times 7/6r. So that's the this would make r prime about 7440 kilometers, or and then he redoes that number again, and we get 1.32 miles times
Increase
the
the
square root
level.
of the height in feet. So that is refraction again, considered simply. We're not done yet, though. We're not even halfway through his page. Weird. Gets pretty complicated. Variable gradients. Look at that. Unfortunately, the refraction varies considerably day to day and from one place to another. It's particularly variable over water, which is where this was done. So we're not just looking at simple refraction, we're looking at particularly variable refraction over water, because the high heat capacity of water and the air is nearly always at different temperature from that of the water. So there's a thermal boundary layer in which the temperature gradient is far from uniform. And we can definitely see that the temperature gradient is far from uniform because of the, well, why is that? Let's see. Because of the super bendy crane there over on the left side. See that? Isn't that crazy? Super, super bendy. So worse yet, these temperature contracts are particularly marked near the shore. Oh, well, that's where this was taken. Interesting. Where the large diurnal temperature swings over land can produce really large thermal effects over water if there is an offshore breeze. This is particularly bad news for anyone standing on the shore and wondering how far out to sea a ship or island might be visible. It gets worse. While the dip of the horizon depends on an average temperature gradient, and so far can be found from the and so can be found from just the temperatures at the sea surface and at the eye, the distance to the horizon depends on the reciprocal of the mean reciprocal of the temperature gradient. That's some good math there. Certainly you've done this math. But the structure of thermal boundary layers guarantees there will be a large variations in this gradient, even in height intervals of a few meters. This means that on two different days with the same temperature at the eye and water surface, and consequently the same dip, the distance to the horizon can be very different.
Yes, I agree.
But we're
I
not
agree.
done. Oh, but hold on, we're not done yet. Nasty complications. In conditions that produce superior mirages, there are inversion layers in which the ray curvature exceeds that of the Earth. Then, in principle, you might see infinitely far. There really would be no horizon, assuming that the thermal inversion extended to the top of the atmosphere. Probably not the case here, but you get his point there. To an observer with such a super refracting inversion, the Earth's surface appears to be concave instead of convex. Also, because these inversions are limited in thickness, the distance to which you will see will be limited by the highest visible ray that is trapped in the duct produced in the strong inversion. That limiting ray corresponds to a false horizon, a few minutes of arc above the astronomical one. If the limiting ray has very nearly the Earth's curvature, you could see a long way. If the distance of the curvature is large, the false horizon may only be a few kilometers away. It's all over the place. If the ray curvature exceeds the Earth's curvature everywhere below the observer, every horizontal ray in this region bends down to strike the surface at a small angle. Then no ray can be tangent to the Earth's surface, so there's really no true horizon in the usual sense, only in the top of the duct, which acts as a false horizon surface that looks like an apparent horizon to all observers. Its dip is positive for observers above the duct and negative for observers within the duct. This case was studied by Hasse in 1960. All right. Now, I'll stop my share and go back to yours. You'll have to reshare yours because
Okay.
they can't. So anyway, so after certainly you've covered all of that in your presentation here. So be sure to cover all of your full refraction analysis when you before we get to the conclusion. Okay.
Yes, and the in this website, in this paper, Andrew Thomas Young discussed a lot of different scenarios regarding refraction, right?
Yes.
So going back to the black swan image, which of the refraction effect can bring the horizon 10 times further than it's supposed to be?
Well, if the ray
according to
curvature
the globe.
exceeds the Earth's curvature everywhere below the observer, every horizontal ray in the region bends down to strike the surface at a small angle. Then no ray can be tangent to the Earth's surface, so there's really no true horizon in the usual sense. Only at the top of the duct, which acts as a false horizon surface that looks like an apparent horizon to all observers. Its dip is positive for all observers above the duct and negative for observers within the duct. So, when you said which type of refraction, that sounds about appropriate there, doesn't it, for this image?
So, you're saying because I how should I put this? One of the greatest proof of a globe Earth, right? There's I'm sure everyone has heard of it. Ships going over the horizon, and the horizon is a physical sphere edge that is capable of blocking boats and buildings. But as you see, the horizon varies, and not just vary, it exceeds its geometry 10 times. So
Yeah, as Andrew Thomas Young, subject matter expert, has stated. Absolutely, yep.
So it's not geometric then. The
No,
horizon is not Earth curve then.
It is the apparent horizon, as subject matter Andrew Thomas Young
Yeah.
said. It is the apparent horizon.
All horizons are apparent, even for a globe, because you can vary your height and then you can see further. So
because we can only see apparent things. We cannot see the geometry, right? So to get the geometric horizon, we would have to have from the observer's eye out to the geometric horizon a perfectly rigid structure that doesn't bend at all, which is a pretty difficult thing to construct.
I would say that is impossible because air is always there, right? Or air is always present.
Absolutely.
So you cannot have a day where there is no refraction. But the problem for the globe is the horizon is claimed to be the globe is claimed to be the sphere edge of the globe. That's the horizon. Your horizon is the geometric horizon. That's the problem.
No. Don't put words in my mouth. We cannot see the geometric horizon. We can only see what is apparent.
Sorry. Can you repeat that again? We cannot see the geometric horizon.
We do not see the geometry. We see what is apparent. Yes, everything that we see is affected by the light. So the geometric horizon, which Andrew Thomas Young, subject matter expert, speaks about, is only in the first instance there where he says no refraction. That is, the geometric horizon neglecting refraction is what is the geometric, which of course there is never no refraction. As you said, there's always refraction, so we always see a refracted and apparent version of it. So we don't look for the geometric horizon, we look for the apparent horizon. So the apparent horizon that we see here is obviously very, very modified. And just like Andrew Thomas Young, subject matter expert, says, there is no true horizon in the usual sense. Only the top of the duct, which acts as a false horizon surface that looks like an apparent horizon to all observers. That's what we see. Perfectly matching subject matter expert Andrew Thomas Young's predictions.
So when ships disappearing bottom up, it is not going through the curve of the Earth then.
Oh, of course, it is obstructed by something. Something is certainly obstructing it, yes.
Let me put it this way. The horizon is not the Earth curve.
It is the obstruction.
It is not.
It is the obstruction of the water in the way.
It is the obstruction of the water. So the horizon is not the Earth curve then.
It is water obstructing the bottom of an object.
Well, because this is a claim that everyone uses.
Yes, it is the obstruction.
No matter Neil
Yes,
deGrasse Tyson, no matter
the light,
Brunei,
the light
everybody
is
says.
being blocked from getting there because there's something in the way.
What? Why is it blocked? Is it the sphere age?
It is the well, I can show you a nice image here. Let's see here.
Yeah, you can use the picture of Andrew Thomas Young.
All right, no, I have a nice one here. I'm going to turn off. I'll share it to you. This one I made here. I like this one a lot. Right there. All right, you see that?
Yeah.
Okay.
Batman.
That's Batman. Yes. So the bottom is obstructed by the bulge there, which on this image is HG. HG, that line HG is the bulge. That's what's obstructing the distant object. Now this all is no refraction. This is the no refraction version of the image. So
yeah, so the line AFB is the tangent point to the edge of the sphere.
Yes.
That's your horizon. That is your horizon.
F is the horizon, right? F at F. Yes.
Yeah, horizon is where the sky appears to meet at the ground or the sea.
Yes.
So yeah, we have one horizon, and your horizon, if you live in a ball, is sphere edge. But now you're telling me that the horizon we see is not the sphere edge.
No, Andrew Thomas Young is telling you that. The subject matter expert that you cited is saying that
you agree with him. And you agree with him.
Yes, that the visible horizon, the apparent horizon, is all we get to see.
Yes. In fact, in the Black Swan photo, the horizon is beyond the capability of the globe Earth.
No, not at all. Not at all. According to Andrew Thomas Young, not at all. Let me bring back, I'll read it again. You must have forgotten. If the ray curvature exceeds Earth's curvature everywhere below the observer, every horizontal ray in this region bends down to strike the surface at a small angle. Then no ray can be tangent to the Earth's surface, so there's really no true horizon in the usual sense. Only the top of the duct, which acts as a false horizon that looks like an apparent horizon to all observers. That is what's happening in this picture here. It's a false horizon. That's what we're seeing here. The false horizon. According to your subject matter expert, Andrew Thomas Young.
This is not the case. How can you push back your horizon but not the crane? You see
what do you mean push back the crane?
The crane should be hidden.
Why should the crane
by the curvature, right?
Why should no, I'm sorry. You were the one that didn't want to talk about the crane. You're the one that only wants to talk about the horizon. All right, so let's go back to the horizon. There is a false horizon, as specifically stated by your subject matter expert citation, Andrew Thomas Young.
It is not a false horizon. It is the horizon. We only got one.
Oh, well, you must have
the horizon is just like the Earth curve. It's that simple.
Fung, you must have forgotten already the citation from your subject matter expert citation, Andrew Thomas Young. The ray curvature. If the ray curvature exceeds Earth's curvature everywhere below the observer, every horizontal ray in the region bends down to strike the surface at a small angle. Then no ray can be tangent to the Earth's surface, so there's really no true horizon in the usual sense. Only the top of the duct, which acts as a false horizon surface that looks like an apparent horizon to all observers. Your citation. Fung, your citation.
Yes, and I agree with him.
Okay, good. So then this particular false horizon is what he's talking about. That's what he's talking about. The false horizon because of extreme refractive conditions. So there we go. Now, did you do the analysis of refraction or on this at all?
No. Can you put back your Batman photo?
Right there.
Yes. So what is the point of your photo then? If the horizon is not a geometric horizon and we cannot see the geometric horizon, always, because
well,
there is
yeah,
always refraction. So
sure.
what are you
Well,
what are you guys talking about
yeah, well,
when
let
you
me,
say a certain height of the object is hidden
absolutely,
by the
I'll show
earthquake?
you. I'll show
What
you.
are you talking about?
Right here, we have back to subject matter expert Andrew Thomas Young's graphic. You see the diagram, line OG, original gangster, right there. See that line? That's the non-refracted one, which is similar to mine, where I have no refraction listed, right? Then he has this one here. Look at this. He has that curved line OH. You see that?
Yes, I
OH.
do.
It's curved. It goes past OG. So you can see the horizon past OG. OG is in the same spot as before. H is farther. You can see farther. This is, of course, the simple case. Right? Now, if the refraction is significantly more aggressive and variable and has ducting, then not only will you see past H, but you'll see multiple horizons, like false horizons. As your subject matter expert citation, Andrew Thomas Young, mentions. So,
Yes, that horizon you're referring to is standard refraction.
yeah, that like I said, refraction considered simply.
Yeah.
So
The bendy line, the bendy line is.
the variable gradients get significantly
Hold on,
more
hold on. You just
complicated.
show. Hold on, Mike. Hold on, Mike.
Mhm.
You just showed the picture showing a standard refraction. Now you are going to
Yep.
talk about other things.
Yes.
Yes. On in
Certainly,
this. Yes.
this is not standard refraction. No question, this is significantly more complicated than standard refraction.
If it is
So,
not standard refraction, then the horizon should appear in front of the
oh no,
of the
it's
frame.
much more refraction than standard refraction. So standard refraction lets you see a little farther. Much more refraction lets you see much farther. In fact, you must have forgotten it. I'll read it again since you seem to have forgotten it. Again, only the top of the duct, which acts as a false horizon that looks like an apparent horizon to all observers. That's what we're seeing here, Fung. Your own citation says that we're seeing a false horizon that looks like an apparent horizon to all observers. So, what's your point? Your own citation says that we should see a false horizon in extreme refraction conditions, which is exactly what we see. Thank you very much. Do you have any actual analysis of the refraction?
Yeah, because to my understanding, the refraction doesn't push back doesn't push back to
Well,
where
then you didn't read your own citation here, because clearly even in the simple case it pushes back the horizon, and in the complicated case we see false horizons all over the place. So, your own citation, your own subject matter expert, Andrew Thomas Young.
So yes, so we can all agree that the horizon we see is not the geometric horizon.
Why are we backing up? We've covered that first step. That was the no refraction version, which was a while ago, which was half an hour ago, Fung. Half an hour ago. Try to keep up. Okay? So your own citation, all right? I'm not going to give you any out on this. This is your own citation, Fung.
Mm-hmm.
Your citation. That looks like an apparent horizon to all observers. It is a false horizon surface. We are seeing a false horizon surface according to your own citation. And who is that?
The subject matter expert, Andrew Thomas Young, our favorite guy.
You don't have to repeat it 10 times. I
okay. All right, so let's move on then.
The horizon, so we can both agree that the horizon is not the geometric horizon, it's not the Earth curve.
All right. Do you? Correct. We've already gone past this, Fung. What are you doing?
Yeah. Yes, I'm agreeing. I'm agreeing with you. Every word you said and every word that Andrew Thomas Young said.
Excellent.
Yes, this is not the Earth curve. This is another picture taken by taken by the same guy on a different day.
Yeah.
You see the horizon is closer.
Yeah.
It's closer than before.
Yep.
Correct?
Yeah, because refraction happens.
Yes.
Heavy
and it is
refraction
not,
with crazy ducting and all sorts of effects. And here is a non-crazy refraction
yes,
with
I
just
get it.
some consistencies. Yep. So
I get it. So the horizon is not Earth curve.
in this particular instance, the horizon is a false horizon, according to subject matter expert Andrew Thomas Young.
So sometimes the horizon is the Earth curve, and sometimes it's not.
According to Andrew Thomas Young, subject matter expert, yes. Only the top of the duct, which acts as a false horizon surface that looks like an apparent horizon to all observers.
Yeah, I agree.
Okay.
I agree.
Okay,
The horizon,
but why do you keep rehashing it then? I've already covered it. It's a false horizon. According to your citation, we see a false horizon. So now what?
Because this is my argument. I also agree that the horizon is an Earth curve.
It's not Earth curve.
Okay, it's not
Well,
Earth curve.
then what is it?
And how are you going?
Then what is it?
How are you going to determine the radius then using Earth curve?
Oh, I don't determine the radius by looking at the horizon.
Well, Alberini did.
I'm not. My name is not Alberuni, so I didn't.
But your globe belief based on the certainty of the radius of the Earth and
oh yes.
How?
So right here
No?
I have 6 radius of the Earth measurements. None of them use the horizon to measure the radius of the Earth.
Okay, let's go through it. Let's see how
Right.
are they going to derive it.
This one right here, the transcontinental triangulation of the American arc of the parallel.
Of the American arc of the parallel, I'm
Yep.
not familiar.
Well,
How
the
do
deal.
they do it?
You
How do they
accused
do it?
me. You accused me of using Alberundi to get the radius of the Earth. I don't
that's-
use that. I use the transcontinental triangulation and the American arc of the parallel to get the radius of the Earth. Is one of them.
Okay, sure.
And that
sure.
and that
How
one
do
and that one got 6,377,912 meters. And because there's two, there's the polar radius and the equatorial radius. The other one is 6,356,309 meters.
I'm sure it is pretty close to what Alberuni gets. And may I ask?
Again, why Alberuni?
how
When
did
did I bring up Alberuni? I didn't use Alberuni.
Because this is the globe rhetoric. You are defending the globe, right?
It's not my rhetoric. Why are you putting words in my mouth?
It is the globe belief. Are you defending the globe, or are you
all
just
all
attacking
flat
the
earthers? All flat earthers think that you're accelerating upward at 9.8 meters per second squared. That's the flat Earth rhetoric, correct?
No, it is not. It is what.
Oh, well, let me just put those words in your mouth there, Fung. Let me do the same thing to you. That's what you believe, right?
Sorry, the globe belief is a firmly established belief among the modern times.
Okay. Then
So
use a modern measurement. Go ahead.
You're dismissing what the previous ones have done.
Oh, well, you're dismissing the Flat Earth Society's belief that
Of course, I dismiss him. I've got no problem dismissing it.
No. That's your personal rhetoric, Fung. I'm going to put words in your mouth if you're going to put words in my mouth. That is what you personally believe, Fung, and you must absolutely back it up. Fung, why do you believe that the Earth is accelerating upward at 9.8 meters per second squared?
I don't.
Oh, well, then why would you put words in my mouth? Don't do it. Tell you what, let's agree to not put words in each other's mouth. I'll tell you how I got the radius of the Earth, and you tell me whether or not you think that the Earth is accelerating upward at 9.8 meters per second squared. Got it? Agreed?
Okay. So can we both call bullshit on those claims? I call bullshit on the Flat Earth Society. Can you call bullshit on Alberuni?
No, I will just cite what I cite. How about that?
You have to back him up, right?
No, I will cite what I cite.
Different.
This is the measurement of the radius. Fung. This is the radius of the Earth measurement. Okay, this is the one I cite. So,
how did they do it?
How did they do it? What they did is they measured along the 39th parallel from coast to coast in the United States. They got that entire length and I have the numbers right here. On pages 869 to 871, they have the final analysis. They measured 4,182,227 meters on the arc of the parallel. It was between two particular lines of longitude for a total of 48.279953 degrees, giving and then you can use the circumference to get the entire radius of that particular line of latitude all the way around the Earth, which is and we use that formula there, right? Giving the entire the circumference of the 39th parallel all the way around the Earth is 31,184.8 kilometers.
So what they did is they measured the distance from one coast to another.
Yes.
And then they assume it is a sphere.
No.
And then they calculate the arc.
Yeah, they calculate the arc. It's not an assumption that it's a sphere, though.
Huh?
They are not assuming that it's a sphere.
How did they come to the conclusion that what they're measuring is actually an arc?
Because every time they measured a triangle, you know what they got?
What they got?
Spherical excess. I'll give you one of them right here.
Spherical essence?
Excess. So right here, here's from that particular survey. They have these three peaks in this is in Western United States: Peak Ibapaw, Peak Pilot Peak, and Ogden Peak. And they measured the triangle. That's how they do surveying. They measured a triangle, the angles between each of them, and they sum to more than 180 degrees. Now, on the surface of a plane, a triangle sums to 180 degrees. On the surface of a concave surface, triangles sum to more than 180 degrees. And these triangles all sum to more than 180 degrees. Let me show you here. You see where it says 62.160 there?
Yes.
Okay, that is the spherical excess. That is the number of arc seconds over 180 degrees. So we have 62 arc seconds over 180 degrees. The next one down, we have 39.915. You see that?
So let me ask.
I'll keep going. Just a second, though. I want you to see this number. Item 30 here, 61.951 arc seconds more than 180 degrees. It continues 13.091, 71.871. All of those measured triangles are more than 180 degrees.
For the triangles.
Therefore, hold on. Therefore, the Earth cannot be flat. Every single one of them has a spherical excess, which can only happen on the surface of a convex surface. Go ahead.
So the 3 points of the triangle are they the 3 points mentioned say like on 28? The first one is a place, right? I'm just trying to establish where are the 3 points they're making their triangles.
Yes, the Ibapaw, Pilot Peak, and Ogden Peak are the three for the for number 28.
They're all mountains.
Yes.
And have you considered refraction?
Yes, refraction for horizontal measurements is not a factor because it's not horizontal. It's you can look up how they deal with refraction in surveying for zenith measurements and what they do for azimuth measurements. And for azimuth measurements, they do not include it because there is except in cases like inside of a cave, there are things that they do to deal with refraction because when you're near the wall, it can affect it. But when you're in the open air, there is no horizontal refraction.
How come you can dismiss refraction when when you
Because
say
because I've read surveying books and how they do it.
you read surveying books and they're telling you that they are not accounting for refraction.
That's right. Now if you were to go,
But
if you
in
were to
reality,
what,
in your model, you just told me 10 minutes ago there is always refraction, and the refraction is
vertical,
capable.
vertical, absolutely. Yep.
And the refraction is capable of bringing the horizon 10 times more than where it should be.
Yeah,
So
and
how come they are not accounting for it?
Because horizontal measurements, you don't account for it because it's not a factor in horizontal measurements.
Well, on the Black Swan photo, it is also a horizontal
No,
observation.
the Black Swan is a vertical.
Is it?
Yes. You want me to?
It's
I can
looking-
show.
it's only-
I'll show you the
looking
picture
out.
again since you seem to have confused it. Right here, here it is. O is the observer, and you
No,
can
I'm
see the
talking
O.
about
O
the-
is at as an elevation above the surface of the Earth, looking down towards the surface of the Earth. That is a vertical observation.
The H,
Yes.
the H in
Yep,
the Black Swan is
Yep.
only 1 foot. It's only 1 foot.
It's
It's only 1
traveling.
foot.
Yes. It's traveling through, but it is greatly affected by vertical refraction. So, you could in your ignorance, you could try to argue with surveyors, but I think that you're not going to get very far with that because surveyors know much better than you, unless you have a long history of surveying that you can somehow cite to convince all of us that you know more about surveying than surveyors. Is that the case?
No,
Fung?
I'm sure.
Or
I'm
you're not a surveyor. You don't teach surveying at a university. You haven't written books on surveying. You don't have 20 years of experience as a surveyor. No, then I will not be paying one lick of attention to any claims that you make about horizontal surveying. In fact, what I will do is I will look at the books that I've read, the surveying books that I've read about horizontal refraction.
I'm not disagreeing with them.
Oh,
I'm
good.
just
Okay,
pointing-
so
I am just pointing out that the measurement they take doesn't account refraction. But
as
it is
as
the
it
same,
must not.
It is the same
they should not.
refraction you stress about.
No, it is
for at
it
least
is
20 minutes.
the opposite
It
type
is
of
not
refraction.
consistent. It is
It
not
is-
consistent.
It is the opposite type of refraction, Fung. Like I said, since you are not a surveyor, I will not pay any attention to your stupid and worthless opinion on how surveyors actually really truly do surveying. That's their job, right? You're not a surveyor, so I'm ignoring all of your opinion on it. So, anyway, here is how they know without a doubt that there is no that they're not on a flat surface. The other thing, just to give you a little bit of what about refraction? Well, if there was refraction, it wouldn't do the same thing. If it caused everything to shift to the right, maybe, right? Then all of the measurements would be shifted to the right. All of them. It would be consistently shifted to the right. That's not the case.
According to your refraction, apparently it doesn't. It only affects the horizon, and the cranes in the Black Swan photo stays where it should be, because the cranes are demarcations for the distance.
Yeah, I mean,
they're still there.
Okay,
Only the horizon loop.
All right, I'll read it again from your citation, Andrew Thomas. Oh, wait, let me have this.
Andrew Thomas Young, San Diego State University, Astronomy Department. The subject matter expert.
There we go. Subject matter expert. Only the top of the duct, which acts as a false horizon surface. That looks like an apparent horizon to all observers. So
And
again,
this is my point.
you
This is
keep
my point.
forgetting it.
The Earth
Fung.
is not geometric.
Yeah, absolutely. Nobody has a problem with that. It's a false horizon that you're seeing. So now you were wondering about how they got the radius of the Earth, and here's how I'm telling you. Number one, they're not assuming that the Earth is spherical. They know that the Earth is spherical because it cannot be any other shape, because every single triangle has a spherical excess. Not just does every triangle have a spherical excess, Fung. Not just that. It goes much, much, much more than that. Let me show you. Spherical excess you can calculate if you know the length of the sides of the triangle and the angles of the triangle. You can actually know the radius of the surface that you're sitting on. See this formula right here?
Hmm.
Cosecant of C over R equals, and I'm not going to read the whole thing here, right? This formula there. Now you can solve for, you can see that R is in there, the radius of the Earth is in there, as well as the lengths of the sides and the angles. You can solve for R, for the radius of the Earth, right? Guess what I did? I did that. In fact, I have from the good Dr. Clive Wells, he he even derived that formula for me. I have it right here. Right there. So that particular formula that was on that page isn't just something that came out of nowhere. I have the derivation for it right here. Okay.
Mm.
And then we can go to, there it is. The formula, let's see. Let me see if I can zoom in for you so you can see the formula that I used. I used Wolfram Alpha to solve for R, which is right here. R equals C all over, and then there's this big mess at the bottom. So I put that into this right here, a spreadsheet. And I took the peaks from that survey. Let's see. Let me find one here. I think I put in the right here. No, I didn't do the IBAPA and where'd it go? This one here. I haven't done this one yet. IBAPA pilot.
It's okay. It's okay. I believe the
right
numbers are accurate.
Okay. Well, let me just show you. I just want to show you right here.
But there's a problem, Mike.
Right here. No, I need to make it very, very clear that this survey does not assume that the Earth is a sphere. It absolutely outputs that the Earth is a sphere. So right here, 6,373 kilometers is that one particular radius that is obtained from the sides of that triangle and the angles of that triangle. Right? Here's another one. Here's another one. All of these triangles output the radius of the Earth, the same radius of the Earth. So it's not even that it's on the surface of a unknown convex shape, because every single triangle gets the same radius of the Earth. So there, that was all about how did you get the radius? That's the answer to the radius. Not only did they do the calculus, or not calculus, just trigonometry, to get the circumference of the 39th latitude, and then do the trigonometry to get the radius of the Earth around the equator. Not only did they do that, but you can take their numbers for the measurements of the triangles, and you can plug it into the trigonometry, and you can get the same radius of the Earth. So that's how they did that.
Okay, so the survey is measured in triangle. A triangle needs 3 straight lines, but in your model you can't have a straight line because every line of sight is bent. So how can they get the correct measurement?
Well,
I'm not saying
that's where you don't understand spherical triangles. Again,
according to you cannot get a straight line anywhere.
Right here. You see this diagram?
So here's the problem.
Fung,
you need
Fung. I'm going to explain
a straight line when you need it.
Fung, I'm going to explain it to you right here. Do you see this diagram? Do you see this diagram here?
Yeah.
Observer at point A.
Yeah.
A to C is a straight line. You see that?
Well, you can't have it. You can't have it.
Well, I do. It's a straight line. And A to E is a straight line.
According to you, it can never be a straight line.
No, according to me, they are straight lines.
Huh?
Yes.
You just told me every line of sight is bent.
No, I didn't.
15 minutes ago.
Why are you lying?
When you are addressing the Black Swan photo, you told me
Because yes, because the line is curved down like that. Yes, definitely. But
Yeah.
we're doing just the let me get that
So
up again.
it is straight. It is straight when you need it
So-
them to be.
Well, this is just the horizontal aspect of it. That's all that we're looking at. And again, surveyors, not you, surveyors say that azimuth measurements are not affected by refraction. So these are straight azimuth measurements. So
Yeah, that's exactly my point. You cannot have a straight line when you want them to be. In your model, it's always curved. You can never get a straight line.
Why are you putting words in my mouth?
Just told
this is
me.
just the
What
azimuth.
happened?
Just the azimuth measurement.
Yeah, when you're doing math, you want all lines to be straight, including your earth curve calculator, where how many feet of the building is blocked by the geometric.
Are you unaware that it is
the Batman photo? Remember?
you seem unaware
when
that
I presented the
Fung,
Black Swan photo, you
Fung,
said it's curved.
Fung, you seem
how does that
unaware. You seem unaware that mathematicians are capable of figuring out how to do things with curved lines.
But they didn't account for refraction, which is always there. That's the problem.
Yeah, in an azimuth, in an azimuth measurement, you do not take into account refraction because it doesn't impact it.
Well, that's the problem.
So you are smarter than all surveyors. That's
I'm not
what
smarter.
you've just declared yourself to be more knowledgeable than all the surveyors. Fung, could you please give us your credentials to back up your claim that azimuth measurements need to take into account refraction in direct contradiction to the entire field of surveying? Please give us your. Do you even know what an azimuth? Do you know what an azimuth measurement is?
Mike.
Fung, do you know what an azimuth measurement is?
No, I don't. You can tell me, but
Yeah, it's
the point
the
is,
horizontal component of a measurement. It's not the vertical. It's only the horizontal component of it.
Point A to point C is traversed in a vertical fashion, right? Point C is higher than point A, right?
It has no bearing on whether it's higher or lower than point A, because all that you're measuring is the angle between C and E, the horizontal angle between C and E.
You are either, if you agree to the diagram you just show on screen here, then you cannot say the light is bended. You cannot have it both ways.
It is not. No, I'm sorry, Fung. You again are not a surveyor. You do not have the credentials to declare that all of surveying is wrong.
I'm not saying.
You absolutely are. Yeah, you absolutely are.
But you are holding two positions here.
No, I'm not.
On one hand, you are saying that point A to point C is a straight line. On the other hand, when I present the Black Swan photo, you say all lights are bent. So which one is it?
I'm measuring an azimuth measurement is the look at on screen there. It is angle.
So light is not bended.
Tell me the measurement that the azimuth on screen there. What letter is the azimuth measurement?
Well, if you told me what an azimuth.
I already did tell you, but you seem to have forgotten. Your short-term memory is a problem. An azimuth. All right, you'll have to shut your freaking mouth in order to learn what an azimuth measurement is. Are you ready to learn? Free education for you, Fung. You just got to shut up. It is a horizontal measurement only, not any part of the vertical measurement, just the horizontal measurement. That is an azimuth measurement. Straight north is 0. Typically 0 degrees. Straight east is 90. So if you're going to measure the azimuth between due north and due east, it's 90. That's an azimuth measurement. Okay. On this particular diagram, triangle CAE. Do you see that? CAE. The azimuth measurement of CAE is denoted by arc B, lowercase b. Do you see that?
Sorry, I've got a call. Yes, I do.
Okay, so that is the azimuth angle. It is not affected by refraction, according to the entire field of surveying. That's it. Okay, so if you're going to try to argue and claim that we can't use that, then you're going to need to have some citations.
No, I'm not saying that we cannot use that.
Excellent. So we can use horizontal measurements, azimuthal measurements to measure triangles, just like these in right here. So, spherical excess, measured, absolutely cannot sit on the surface of a flat surface because every single triangle that they measured has a spherical excess. Every one of them. Got it?
Yeah, I think I got it.
Okay, that's how they measure the radius.
I don't know. It's the only problem is I don't know if that's the only explanation of why the triangles is greater than 180 degrees. I'm not sure if the Earth is a sphere is the only explanation for that. I don't know.
Well, what would be the alternate explanation for
every
single triangle having a spherical excess? And not just every single triangle having a spherical excess, but every single spherical excess triangle, when you solve for the radius of the Earth, giving you the same radius of the Earth. Right? Do you wanna answer your phone?
Wait.
I'll give you a second. Oh, should I feel bad for him? I was prepared for it and he wasn't. Let me tell you what, I'm going to read a few super chats.
I'm a stupid flat earther, right? And I'm just a loser.
Oops. How did that happen? All right. Let's go here. 3 Ron says, congratulations, Fung, you discovered refraction. All right. Oh, let me do this. That's the wrong picture. PJCnet does not need to get blocked unless he's being rude, which he doesn't. He's not rude. So don't block PJCnet mods, please. Earth is Life says, ask him where he got his Black Swan argument from. I will. Fung, are you back?
Yes, I'm back.
All right. Where did you get this? I'm reading a few super chats, if you don't mind. Where did you get this Black Swan argument from? Did you make it up?
No, of course I don't. It's on various YouTube channels.
Which one? Which one?
Nathan Oakley and Mitchell from Australia.
Really? You didn't? Yeah. You forgot the one that invented it. Let me do a little thing from him.
So, Andrew Thomas Young, San Diego State University Astronomy Department. The subject matter expert.
Quantum Eraser.
There it is. Yep, that's from him. He's the one that cites Andrew Thomas Young. So, all right. So it's all from Quantum Eraser. You just read the script from Quantum Eraser. So, Indy Tiger says the oil rigs were designed by Salvador Dali. You know who Salvador Dali is, right?
No.
No, he's an artist. He was known for making crazy looking bent things in his art.
So, the argument.
Hold on, no. Let me read through a few more super chats if you don't mind. How about that?
Okay.
All right, because a couple people asked us some questions. Cretan Ball says, Fung, go back to bed. This isn't going well for you. It's been a little tough, Fung. Steve6464 says, hasn't the Black Swan photo been debunked so many times by now? That swan surely must be dead. It is. The poor thing's been roasted. There's just nothing but ash left. Alyssum says, may I suggest a nice Vermont with that swan? I'll have some moonshine. with it, if you don't mind. Mm-mm. And Tim Tully says, Hail Sagan. That'd be Carl Sagan. You know about Carl Sagan?
Yeah, I
Yep.
do.
All right, let's see. Alyssum says, my goldfish has better short-term memory. Yeah, you did keep forgetting about what Andrew Thomas Young said. 3Ron says, Fung, do you know why we don't see the geometric horizon?
Is it ask me?
Yeah. Why do we not see the geometric horizon?
Because there isn't any.
No, because it's apparent. We only see through the air what's through the air. Gears of Yoda says, you're awesome, MC Toon. Well, thank you very much. You're awesome too, Gears of Yoda. Cinnamon Control says Al Burundi got the right answer because he measured from high altitude, where refraction is highly regular and predictable. Get high! Yay, get high! Delcos Man says, I'm also obstructed by the bulge. Maybe he's eaten too much. Al Margiu says, it is the effect of Earth curve. It just happens that you can see farther due to refraction. Are you in the mirror, Fung? When you look in the mirror, do you see you or do you see the apparent you?
It's not the same thing. It's not the same thing.
Oh, it's not? You see the actual you, the geometric you, when you look in the mirror? Not the apparent you. Your eyes receive photons. They don't receive geometry.
Okay. Are you done with the super chats?
Almost.
Okay.
I don't want to get too far behind. Got a new member, Andrew Findley. We got Alyssum says, almost dropped an F-bomb there by a PG-13. I did not. What are you talking about? I said freaking. Gary IOW's been a member for 11 months, and then he says, holy hell. And Stringer News 1 says, 17 months, I have no life. You do too. This is your life. You can't go anywhere. You're trapped. Alyssum says, navigational distance calculations confirm R. Done. It's a good point, Fung. How do you calculate the distance between points on the surface of the Earth? How's that done? Like when an airplane does it. What do they do?
I don't know. How?
The Haversine formula.
Sorry? What formula again?
It's called the Haversine formula. We can get different day, different topic.
Oh, it's not relevant.
Yeah, it's relevant because it's what they use for navigation. So anyway, Pate Laro says, explain to Fung how a bow can look straight from one angle but crooked from another. Have you ever, I don't know how it is for you, but I go to the hardware store and buy a 2x4. Have you ever bought a 2x4?
No.
I suppose dimensional lumber might be a little different dimensions in Hong Kong. Well, when you look at something like this, if there's a curve, you don't see it very well. So what you do is you look at it this way, right? And you look down it if there's a curve.
I can see it. I can see it.
Oh yeah, hold on. I'm showing right here. You look down something, you can't see if there's a curve this way. So you look down it like this, and if there's a curve on it, then you see it.
Yeah.
He's seeing a different camera than you guys are at home.
Okay. Interesting.
William Foley says that the black swan is pining for the fjords. It's had an extended squawk. Anyway, and Great Circle had a message, but it was retracted. So I don't know what this. Or you could tag me on that, I guess. So anyway, Fung, we are caught up on super chats.
Okay. So Okay. First, I must concede that I'm not familiar with spherical exceed. Is it what it is?
Spherical excess, yeah.
Spherical axis.
Yeah.
I'm not familiar with that. So you came to conclusion that the Earth is must be a sphere because the angles doesn't add up to 180. It's beyond 180, and it is consistent. This is very interesting indeed. I might have to look into it. So and for the black swan photo,
Yes.
yeah, for the black swan photo, so you see the apparent horizon is beyond 10 miles, correct? And then what happens to the Earth curve calculator, which always states that there is how much of the building is obstructed? How does that work? Because the Earth curve calculator only deals with the geometric horizon. It doesn't account for the refraction or whatsoever.
Oh, no,
So-
that's completely wrong.
No.
No, it's completely wrong. So if you look at the Bislin Advanced Curve Calculator, right there, it's the first one. If you just search for Bislin Advanced Curve Calculator, it in fact does include refraction.
Do they?
Right here, yes. And it conveniently includes refraction as the coefficient of refraction, K.
That is the standard refraction.
No.
Coefficient
the-
coefficient of refraction is standard refraction.
No,
Am I wrong?
the coefficient of refraction is a number. It is a number. Standard refraction is actually not always the same. It depends on the industry. Some surveyors use 7/6R. That would be
So-
0.167 as for
So
K.
what
Hold
is-
on.
what
Let
is
me
the
let me
value?
finish. Let me finish. Others, U.S. Geological Survey uses 4/3, which would be plus 0.33. But that's if you don't know the coefficient of refraction. Much better to actually measure the coefficient of refraction, but that's hard to do. So you get the lapse rate, and then you can, according to, Andrew Thomas Young, the subject matter expert, you get the lapse rate, and then knowing the lapse rate, you can get the coefficient of refraction, K, which you could then plug in here. Or, let me just show you this. You could,
I can see it. I only see your keyboard.
oh yeah, okay. I'll share it quickly to you. There it is. So you missed this. Here's the advanced curve calculator, and you can plug in your own value for refraction here, depending on the environmental conditions. Or if you don't know the conditions, you can look at some of the previously measured coefficients of refraction, like in this particular paper here, monitoring the refraction coefficient in the lower atmosphere using a controlled setup of simultaneous reciprocal vertical angle measurements. And this goes over several different coefficient of refraction measurements. One that's particularly interesting here is one by Kabashi, Ismail Kabashi in 2004. You see this graph right here. This is a graph of the coefficient of refraction versus time on a sunny day over water. And you can see here where it ramps up. On the far left, we have it being kind of consistent through the night and into the morning, and then through the day, the coefficient of refraction shoots way high. You see it gets almost to 18. And then it comes down, and by sometime in the middle of the night, before it starts to come down to a low level again. So it varies dramatically. So if you want to predict the distance to the horizon or the amount of a hidden object across water, the conditions vary dramatically. It's a really poor way to predict to do anything because the conditions vary so much. But if you do insist on doing it, then you should definitely do it on an overcast day, because on the right here we can see this graph just for reference, on the left, the graph goes from 0 on the bottom to 18 on the top. That one that moves a lot. On the right side, which was on an overcast day, the bottom of the graph is 1 and the top is 2. This hardly varies at all. It's super consistent throughout the day when it's overcast. See that?
Yes.
So
So you cannot. Sorry.
So this particular video was taken late in the day on a sunny day, right over water near the shore. The absolute most aggressive time for refraction, as measured empirically, right here on the left side here, that big old, that big change in coefficient of refraction there.
So we can no longer say that the horizon is the geometric horizon, because this is what I heard all
Oh my
along.
gosh, that was an hour and a half ago, Fung.
Yeah. So we cannot say that anymore, can we?
We never did. Nobody ever said that you can see the geometric horizon. You can only see what happened, what's photons.
Okay. So at least something's cleared up.
So we've
Because
got somebody in the chat here says, stuck in the YouTube matrix, that says, I have been surveying for 22 years. Let me at him. Somebody wants to talk to you, Fung. Maybe you go a little more and then you want to talk to him. I don't know. It's up to you. That wasn't the deal. I don't like to change it if you don't want to.
Is he going to tell me about surveying? Because I know nothing.
Well, that would be your chance to learn about surveying.
Yeah, sure. Go ahead. Oh.
All right. Well, send me an email, stuck in the YouTube matrix. All right. So there's that. So what were you wanted to say something about this? I mean, we already covered, and if you're going to just talk about the geometric horizon and the false horizon again, it's just going to be rehashing stuff we've already covered.
Well, yeah, it's pretty much done for me, because the globe claim is always be the horizon is the geometric sphere edge. That this is the claim that I always hear. So, but now all of a sudden you say nobody claims it. It's very
Nobody
amazing.
claims the geometric horizon.
Yeah, the horizon is not a geometric horizon. Yeah, it is very new to me.
The apparent
I- I-
horizon. The apparent horizon is not the geometric horizon. The apparent
Yeah,
horizon is
every
the
horizon
apparent
is
horizon.
apparent.
Yes,
Yeah,
absolutely.
I get it. I get it.
Yep.
I get it. So, wow.
Here's the problem. Quantum Eraser is lying.
Yeah.
Nathan Oakley is lying. They don't know what they're talking about, or they're just making stuff up. Nathan Oakley, he only does it for money. Fung. That's all he
Well,
does.
he's a YouTuber.
Yeah, he only does it for money. He doesn't care about truth. He just cares to make enough money so that he doesn't have to go back to being a delivery boy. That's it. Fine. Don't be fooled by him, though, Fung. He's just fooling you. So you all you did is you took the recipe given to you by Quantum Eraser, and you just tried to use it on me, and I knew everything that he was going to talk about. Because I've studied this. And Fung, not that it's a bad thing, right? You didn't study it. You didn't actually read the stuff by Andrew Thomas Young. You heard Quantum Eraser say Andrew Thomas Young, subject matter expert, but you didn't actually go read the stuff by Andrew Thomas Young. Maybe you should do that. Maybe you should do what people say, do your own research, right? I think that you can learn, Fung. I think that you don't need to listen to these people, because they're leading you down a path that's not going to do good for you. Right?
I don't know because the horizon isn't geometric. This is really the first time I hear it. I don't just watch Nathan Oakley shows. I've watched many other shows.
Yeah.
All of the globe proponents always states that, oh, you see how much of the building is hidden by the Earth curve.
And that
And
goes
that
to
Earth curve is the horizon. And now you're telling me that the horizon isn't Earth curve.
Well, here's what we don't see this one. We don't see the no refraction version.
Yeah.
But this
is the only picture that always shows up.
Yeah, it's always the
the
simplified one. And I gave you the simplified one right here, right? I didn't include curvature in it because it's hard. It makes it harder. And when you're introducing the concept to somebody, it just messes it up and makes it more complicated. So people give you this, right? This is actually the base case because there's always some refraction. And if conditions aren't chaotic, it's a small amount of refraction and you see that, right? And you can see that in this picture here too, right? This is the crane over on the left side, nice and straight. If you look really close, there's a little bit of wobble to it. Not a lot, but there's a little bit, right? So that's not quite this, but it's close to it. It's more like this. There's a little bit of refraction. You see a little farther. Now, if you look, Andrew Thomas Young has many, many pages here where he goes over a lot of different effects of refraction. And being called the subject matter expert is well earned. He has done a lot of work on this website and put a ton of information on here. Now, you said that you did not do math very much. And if you really want to get into it, there's a good amount of math that you have to do. But you can read stuff. This calculating wave bending is tough. But I think, this one here does a good job talking about, remember K? I said the coefficient of refraction, K? That's this right here. And he goes to standard atmosphere. It's a difficult one because it's never standard. We know it's never exactly standard, but if you don't know what you're looking through, then you need to have some estimate. So people use different numbers. Like I said, U.S. Geological Society uses 4/3. A lot of surveyors use 7/6. But that's actually not even consistent. When you're near water, it's higher. It's always higher. So I sent to, let's see, I'm going to turn off sharing here because I did send a thing to that surveyor. Who is here?
Hello.
Hello. What do you want us to call you?
You can call me Stuck if you want.
Stuck. All right. We've got
That
Stuck.
works for me. How are you guys?
I'm good. I've been doing a lot of reading on surveying lately.
Of course.
So, and then, you're not, let me change for you, Fung, what you're seeing, because you're seeing my desk. There it is. Okay. So, Stuck, what did you said you wanted to come in for a little bit.
Okay. I want to know where Fung is coming from on this whole, I don't know what he's trying to say. Like, he's confused the heck out of me. You make sense. He doesn't. I mean, the fact that, like, you're looking at these, I don't know, flat, surfaces. You see the curvature of the Earth through the, bear with me here. It's been a long day. I work at 5 o'clock in the morning kind of deal. But, like, you look at across the water and you see the horizon drop. It's been proven. It shows. But it's as surveying techniques as I've seen on yours and FTFE's other channel, right, as well. It applies perfectly. showing why that works. So, Fung, please tell me, what are you thinking on this? Like, where are you really coming from? Because you make no sense.
Sorry, I cannot hear you very well. It's
I'm sorry.
very. I'm leaning my ear next to the computer and I cannot hear you. Sorry.
So I've done all kinds of surveying work of all varieties, and the fact that there is a curve to the earth. End of story. I mean, and surveying is based on many different documents. I mean, just tell me why are you coming from this direction? Why do you say that it doesn't apply?
Why am I saying what doesn't apply? I'm not saying what you've done is incorrect. I'm just confused that because measuring angles needs a straight line, right? But Mike always told me in the entire debate or discussion that you cannot get a straight line. So my only concern is how come whenever you need a straight line, it is a straight line, and then when it is presented something else that contradicts the model, you can apply refraction. That's all I'm asking. I'm not saying that the surveyors doesn't know what they're doing. Of course they do.
Well, yeah, we do. I've been doing this long enough. I kind of understand exactly how all of this modeling works, right down to, or right up to the sky. Where we have a globe, which maps everything completely. So this is what I don't understand. Like refraction side, I deal with refraction all the time, both in the wintertime, in the summertime, and all kinds of conditions. But that doesn't change any of the measurements that you have, because it's all about measuring. It's all about angles and distances. Like, it doesn't matter how much refraction you have. A distance is still a distance, a straight line distance or a vertical distance or a angled distance. It doesn't matter. Okay.
So yes, I heard you. So you're telling me that refraction doesn't affect your measurement. It's only at the distance and the angle that matters, correct?
It will, depending on the methodology of how you measure it. There are ways to compensate and calculate for the refraction. So let's just say, for example, I'm a local site, okay? I'm trying to take a measurement, and I got refraction from the heat, okay? Depending on the temperature and the air pressure that is currently existing in that area, we can calculate an adjustment for that distance based on those conditions. End of story. It's already been proven, and then you come back the next day with zero refraction. You take into account the fact that there is no refraction. You can take the same measurement and get the exact same distance result the next day. And we're talking down to millimeter accuracy.
Got it.
Okay. Do you understand that?
Yeah. So you're actually taking into account of the effects of the refraction.
Right. Because there is, I don't have all the formulas in front of me, and we have now our machines that we use today. You punch in, you tell it the information, and it has all that built in the background. Back in when I first started, that would be taken into account after you come back from the field and do your field work, that you were recorded at this time of day, there was this pressure, this temperature, and you got this distance at that, but then it gets calculated later because we didn't have the technology. Now we do.
Got it. This is the first time I hear such information.
Does that make sense to everybody?
Okay.
Mike?
What's that?
I say thank you.
Okay. I was looking through I was looking through the book Elementary Surveying and Introduction to Geometrics.
Yeah, geomatics, yeah.
Geomatics. Was that your book?
It was one of the many, yeah. And then all the years of experience, of course.
Yep. I have been reading this book.
Mhm. It's very informative, and you just have to, really read it to understand it. Yeah.
Yeah. It goes into good detail on how to deal with, right here, theory of errors and observations, how to deal with the effects of refraction.
Right.
So,
Exactly. That's on that topic. Yes, and then there's a whole bunch of other stuff in there too. But I'm sorry, but this whole curvature of the Earth, and I understand. I know refraction's already done, but the whole curvature of the Earth thing, it's been proven. We have a global model. It's global, and I'm going to say global. I don't care what anybody says. Of our planet, right down to inches on the ground, measured, and like every hill, valley, you name it, it's done. I mean, I don't know what's else to say, on that part.
Okay.
yeah. And I think it's a good point that the field of surveying could not do what they do without knowing the shape of the Earth,
Yeah.
right? They don't go and measure the shape of the Earth every day, right? It's already been done. So you use the known shape of the Earth to deal with adjustments.
And also based on elevation and heights that we are working at, and it doesn't matter where we are on the Earth. We'll also, okay, let me just throw this in there, and this is going to complicate things a bit further. But the GPS network that we have is there are different adjustments made for the different elevation that you are above known sea level. So I don't know the exact numbers, but let's just say I'm right now where I'm sitting. If I'm using my GPS to do my measurements, okay, it'll use a constant of 1.2. If I go 50 miles north of here, which is 300 meters higher, okay, it'll give you a different thing of 1.6 adjustment based on where you're at on the globe and what your height is above sea level. Everything is based on the sea level elevations. That's how everything is calculated, really, when it comes down to it. But anyway, I don't want to dominate the conversation. Yeah.
Do you do you use the automatic leveling?
We do, and we also will do the traditional methodology as well, depending on what we are doing. Automatic is used for a lot of situations for where it's not as critical. If we were to say set, I don't know if you're familiar with this based on what you're reading, Mike. All over our city and almost everywhere on the planet, there are what's called benchmarks. They're basically tablets and whatnot that are set somewhere that won't move on the globe. Okay, that we all surveyors measure to and measure from to get a reference point for what elevations that we're working at in whatever area. Now, you're familiar with benchmarks?
I am. I keep talking. I have a few pictures that I've taken of benchmarks that I'll pull up.
I got one from Australia too that I found just randomly. But anyway, those are measured not usually by just electronic equipment, but the old standard methodology with the eyeball and moving basically from one point to another from 6 different locations that we measure to, and we get a calculated elevation. So there are times when we need to do it and times when we don't. But the technology's gotten better that we could probably get it even as accurate as possible. But yeah.
I have one. I have a picture of a benchmark. Keep going. I have to prep it before I can drop it into the live stream for people to see.
Ask me questions. Fung, speak up. Talk to me. Basically what I want to know. Fung, I got a question for you. All the stuff I've seen between you and FTFE. Fung, do you believe the world is flat or a globe based on all the information that we've given you? Is he still here?
I don't know. Fung, did you hear what he said?
Sorry, I missed that. I missed that part.
Oh, he asked, do you think, based on the information we gave you, what are you thinking right now? Do you think that the Earth is flat or a sphere?
Well, like I said, the surveying is pretty new to me, and then God, I forgot that term again. Something access, spherical
Spherical
access.
excess, yeah.
Yeah, spherical access is also new to me, so I have to go back and look it up. But referring to the horizon, because I've been searching on the internet, in the National Geographic website, it states that the local horizon, also called the geometrical horizon, is the visible boundary between the Earth and the sky. That's the horizon we are talking about.
Yeah,
But now you're telling-
that's
but now
not
That's not the question.
that's not a very particularly semantic definition there, right?
Yeah, but now you're telling me that the horizon is not
like
geometric. So
like I said, that's this answer. That's this version of it, right? The introductory version. The National Geographic, that's popular science. That's not the detailed one. That's not the one for, you know.
So it's wrong.
No, it's
No,
the simplified version. You don't teach calculus to a kindergartner, right? You have to work your way up
So
to
it's-
it.
Okay, no, you didn't answer my question, Fung.
Yeah, because
You didn't answer the question. Do you believe the world-
sorry. Because this definition is the definition I see all the time.
I can
The
send you.
geometric horizon.
Yeah, I can
is
send
the
you a
boundary
surveying book if you want to get very particular. Then you can look up the calculus answer instead of the kindergarten answer.
Okay, so this is not conclusive. Oh, I can say this is not conclusive.
For who?
Okay.
For me?
Okay. So the National Geographic answer is
It's the kindergarten answer.
it's not complete. Can
Correct.
I say that?
Yeah, correct. Yeah, it's not
Okay,
complete.
and the horizon isn't geometric. Okay. It's all very new to me. Yeah, blew my mind.
We use geometry to define things, to measure. Okay? There's nothing geometric about this planet. We use geometry to make a definition of how we measure and locate where we are on this globe.
Okay.
Location and in height. Okay, I'm gonna, Mike, I don't want to dominate. I'm sorry, I apologize, my friend.
I just want to show, let's see, this particular 3805.
There's a term that we use it's called the Cartesian coordinate system. I don't know if Mike's familiar with that term. Yeah, you are. Okay. Fung, look up Cartesian coordinates.
The ECEF?
Yeah. It's one of, yeah.
Yep.
And you'd be surprised. This is how surveyors operate most of our work, is through the Cartesian coordinate system.
All right. I think I found the details on this. Yep, I did. Ooh.
You're doing good, Mike. Thanks.
All right. Hold on. You want to tell me about this? This is, all right. You see that there?
I'm trying to see it. Let's see it.
3805Q. So that particular benchmark. Oh,
I'm trying to read it. It's really tiny. My eyes are bad.
I'll zoom in a little bit.
I appreciate it. Yeah, I'm getting old, man.
There it is. 3805Q.
Okay.
That is this benchmark right here that I
right on.
That I happened to find when we were up near Lake Superior this summer.
Minnesota, nice. Okay, so what do you want to know?
So that's this benchmark that we were just hiking along, and embedded in a stone on the shore was this thing here.
That's right.
And then this is the PDF for it.
Right, so that'll have a hard-coded elevation that was defined most likely through traditional methodology, not electronic.
Yeah.
Okay, and located. It's probably done through. It looks. When was that last updated? 2011. So it's probably done through a GPS network at some point. But the elevation was probably defined by traditional transfer of elevation.
Differential leveling.
Yep.
There it is. Yeah. So let's see. Where's you got the latitude, longitude.
Right.
So vertical order 2.
Which is maybe not. Oh yeah, maybe yeah. It would be more. It would be traditional elevation.
So
yeah.
vertical order of 2 would be it's about the margin of error of the measurement, right?
Right. That's right.
There's kind of three levels.
Mm-hmm.
2 is in the middle, and the particular margin of error is specific. Where is? I'm not seeing that.
Yeah, you're in feet. I work in meters. I'm mentally doing some calculations as we go here.
Oh, you do? Yeah. Oh, yeah, you're in meters. Okay, yeah. In the U.S., everything is feet.
I know.
It's weird. So yeah, 615 feet is the elevation. Looks like.
So so that's pretty high accurate. Yeah. Definitely.
Oh, and this is the non-leveling derived orthometric and ellipsoid height in feet. So ellipsoid meaning that this is based on not a flat plane, but as a spherical surface.
Exactly.
Or elliptical surface. So there it is. Oh yeah, GPS. This one is GPS.
Yeah, so we use the static one in 2013 and 2012. Yeah, okay. All right, yeah.
There it is.
Which gave us rotation and height. Okay. Yeah.
That's pretty cool that over time, every time that they go and update and visit it again, they update the documentation here so that somebody...
you have to, because what happens is, like, as surveyors, we rely on these documents to continue with other work, right? That we would, if we reference this document, this particular benchmark, say, we need to, like if whatever latest one that we have to go by the latest elevation. So if it hasn't been updated in 20 years, we still have to use that 20-year-old data on assumption that it hasn't moved. So, yeah. But I guess this year, because it's by the lake, I guess it's by the lake, eh? No.
Yeah. It was on the shore of Lake Superior.
Most likely probably shifting, because it looks like it has a little bit. 016. No, actually, it's pretty solid.
So, well, there we go. I think that's.
There you go. Anyway,
I don't want to get off into the weeds on that there, but it's pretty cool how particular surveying is.
We have to be.
Yeah, and if you do leveling, you usually start at one and end at another, right?
Well, in order to do a proper leveling job, and like this is why I don't think Fung understands this part, and if he's listening, is that we have to be highly accurate. That's the given. Now, if we were to, like, let's just say we're establishing a new benchmark somewhere, and I've done that a few times, we would actually set it up so that we would locate where we want the benchmark, where it's required. We would set this thing in a case of a rural setting, it would be in, 2 meters of concrete with a brass tablet, buried, has to be below frost line, all these other requirements. Set it, let it sit for 6 months kind of story while it settles in. And then in order to measure it, we have to come in from 3, 4, sometimes 5 different existing benchmarks.
Wow.
And now the thing is, here's the thing, in the traditional methodology, you have to, basically using your eyeball, writing down the heights and then running it out, you can go 20 kilometers in one direction. And then 20 kilometers, you have to go back. You have to make a loop and then do that for each existing benchmark coming into that one. And then you've got a number to work with. This is how the stuff is set up. And again, the curvature of the earth does take a factor in this, for sure. But yeah, that's, Fung, are you listening? Trying to educate him here.
I don't know if he heard much.
I can't get half of it.
Oh.
I got to be honest.
Okay, no, that's fair.
Okay.
I mean, I've been doing this for 2 decades, so I mean, this is second nature to me, all this, right? But I mean, before you start going any further with any more of trying to understand this, like, read and educate yourself, and I think that's what you're trying to do, right?
Yeah.
Yeah.
Right.
Thank you very much.
That's good. And like, what troubles me is I don't think you're really one of them, but oh, the world's flat. No, it's not. And this is what just, I'm sorry, Mike, this really, I've heard a lot of these and it just drives me, you hear my wife, like she knows it drives me nuts. And you can see why, right? Yeah. So get yourself
your job relies on it. Everything would go screwy if it wasn't.
Well, if it was flat, I don't know what the hell. I was trying to figure this out, and like I was trying to do some mental math on some of the stuff that they're been throwing out there based on this visual flat model. And I'm thinking, what the hell? How the hell are you supposed to go around the Earth when it's flat? You know?
Oh,
Yeah,
that actually there is an explanation for that, but yeah.
But it would change everything that you do every day.
It would change the entire everything we do. I mean, but Fung, you got to realize geometry is only used to define what we see and what we need. So when you have, if you can picture, if you had some of those other surveying drawings up there, but like if you've got how do I describe it here? Like two different heights and you're measuring to a lower or higher elevation, you've got the horizontal axis, and that gives you a distance to that point where you're measuring to, and then you've got a height difference, either up or down, and that gives you a vertical distance up or down, but based on that, you have an angle. Thus, you have your geometry. This is how we define it. You understand?
Yeah, I do. This part I do.
If you didn't have geometry, yeah, but there you go. That's it, right there. The raw, yeah. Okay, so if you're looking at the survey instrument on the left, you have your horizontal angle, which gives you horizontal line, which is your 90 degrees. Okay, and then that gives you a distance to that point. Then whatever is measured for the angle, which is I can't read it because it's so small. Infinity? No, A.
Yeah, A.
The internal angle. Yeah, A. Thank you. A, which is an internal angle from the horizontal to that point, that gives you an angle. Then you can calculate based on Pythagoras himself all the information that you need. Once you have the distance and the angle, you can pretty much figure out the rest of it.
Yep. Oh, I went a little too fast, but yeah, there's the formulas for calculating that.
Yeah.
There it is. We've got the elevation, and then it deals with refraction as well.
Okay, the delta. You go back up a little bit. I want to make sure everybody understands that.
Change in elevation. Yeah.
Change in elevation. Right. Okay. HI is the height of the rod. V is your existing elevation.
I think V is the vertical distance.
Vertical distance. I'm sorry.
Yeah, right here. Yeah, it's H times the cotangent of Z, or H times the tangent of A.
Right.
Yeah.
Okay. I'd like to, because I've heard Fung before. I'd like him to learn some of this stuff because then he'd have a better grasp on everything.
Yep.
Read this book.
I can send Fung. This book is pretty serious book. I'm glad to send you the name of it, and I just found the PDF online. All right.
Anyway,
Stuck.
So there you go.
Thank you for your time.
Anytime, my friend. Anytime. If you need me on to argue and get really into it, I'm good. All right.
Yeah.
You know, if you know you can have a tough contestant to deal with, you know, you got my email. Give me a heads up and try and set something up because I would love to go at it with some of these people.
All right. Well, thank you. And we're just over 2 hours here, so I think maybe we can head towards wrapping up a little bit.
Yeah. Nice meeting you, Fung.
Fung, he said it's nice meeting you.
Yeah, me too. Sorry, the voice is not coming through very well. Sorry.
Mike, it was great to meet you.
Yep.
Talk to you.
All right.
Thank you very much. Thank you very much.
Yeah.
All right. All right, thanks a lot.
Yeah, I'm going to bed. I gotta get up at like 4:30. So
Oh my gosh.
yeah. Okay.
All right.
All
I
right.
got a couple more questions here before we wrap up, if you don't mind.
Yeah.
Okay. I hate smartphones. Who probably, do you think that he sent this on a smartphone? Said, I would like to know why Flurfs don't think that Russia would not have called the U.S. out if we faked the moon landing. Russia even almost beat us to the moon.
Well, if you if you know about flat earthers at all, most of us, or I would say all of us, doesn't believe in the moon landing.
Yeah,
So
but do you believe in Russia and that Russia doesn't like the United States in the 60s?
well,
Right?
yeah.
Yeah.
Well,
Now here's another this is even more to the point, maybe closer to home for you. You understand that China and the United States are not getting along very well right now sometimes, right?
well, the Chinese footage is even worse.
No, hold on. China has provided photography of the Apollo landings on the moon.
Huh?
Yeah. China has the highest resolution. Maybe there's more that I haven't seen, but to my knowledge, they have the highest resolution photography of the Apollo moon landing sites, where you can actually see the footprints and the lander and the different experiments that were left there.
Yeah, but you see.
So here's the question then.
Okay.
China, if they wanted to embarrass the United States, wouldn't they be like, oh, there's nothing there? That'd be a huge win for China, wouldn't it?
Well, if you considered the Earth is actually flat and not a globe, then everyone and every country claims to be set foot on the moon. Has to be so to speak in on it. So in that case, it doesn't matter.
But China'd be like, nah, we exposed you. You didn't actually go. But
it doesn't matter. China and United States or the Western world seems to be competing with each other. Sometimes you can say they're
exactly.
sometimes they're enemies in a sense, but to me it's all just part of the control system. China, USA.
So they're not. So China and the United States actually do like each other and actually are on the same side.
It's not about.
Is that it? Because you're from Hong Kong. You're from Hong Kong.
They like each other,
right? You're from Hong Kong.
Yes.
Is there any tension between China and Hong Kong?
Whoa, tension is a very mild word.
Oh yeah. So they're not getting along with each other right now.
No.
Okay.
Not at all.
So I think that maybe for you to suggest that China and America.
Yeah, I don't.
Yeah.
Or to be honest, I don't have any affinity to China or.
Exactly.
It's just me.
Yeah. So I mean, if China had an opportunity to expose the United States not going to the moon, they would be all for it, right? They would love to embarrass the United States, right?
Well, no, it's not like that. It's not like that. So,
no?
like I said, if the Earth is actually flat, so the question will be, so how come every country, every space agency doesn't expose each other? That's your question, right?
Oh, yeah, exactly.
Yeah. And my answer to that is that they're actually on the same team, so to speak. There's no.
Okay, so you do like China. China and Hong Kong do get along.
No, I don't.
Well, which one is it?
Well, the point is there's no China.
Make up your mind.
And America and Britain, they're actually controlled by the same group of people, so to speak. Well, not the conspiracy theory, that kind of Illuminati, that sort of thing, but they're all controlled by the same wealthy, powerful people. That's how it is.
Who in China gets told what to do by the wealthy, powerful people?
How would I know? But if
you just claim that they are. That's the problem.
Well, there's a group of people, I don't know who. Well, who am I? But if you consider if the Earth is flat, then every country claiming to be set foot on the moon has to be in on it. That's very logical. So
China and Hong Kong are good friends. They're good buddies then.
No, it's not the same, right? It's not the same, you know it. So in my mindset, there's no such thing as them. China is at odds with America and the Western world. It's all part of a plan. If you ask me, that's my answer. So
right.
anyway, this is way off topic there. Anyway, you see, like I told you before, I've never used Facebook my entire life until 2 months ago.
Yeah,
until 2 months ago, and then before you, as you know, I did a couple of debates with Craig, a fighter flat Earth. I have to be honest with you. Well, you are far more reasonable and persuasive than Craig. All Craig does is cut me off in the middle of sentence. Yes, that's
I'll be sure to rub it in Craig's face. In your face, Craig.
Well, yes, and then there are several points. There are several things that is completely new to me, including the position of the globe Earth, including the horizon is not actually the Earth curve. That's whole new to me. I thought everybody is claiming that. Every globally believing people is claiming that.
Most people, just to be most of the time, they talk about the simple case. But when you get into complex refraction, well, then you have to do complex analysis, right?
That simply blew my mind.
Yeah.
To be honest, I've never heard a opponent holding this position stating that the horizon isn't the Earth curve. This is very, very new to me. And like I said, there's spherical accession.
To be more pedantic, the horizon is the result of the curve of the Earth, right? And you look at a ball, you see there's an edge on the ball.
Yep.
And something causes that. There's the geometry that causes that. So,
that goes back to the question that since the horizon is not the Earth curve, and it can increase or decrease in the distance from you dramatically, how can they determine the Earth is a sphere in the first place? At this point, this is my biggest concern, because everybody says, "Oh yeah, the globe is proven like 2,000 years ago."
So if you look, there's a few things. If you look at Aristotle is one of the early people to have talked about
the one measuring the sticks, right?
No, that's Eratosthenes.
Okay,
similar sounding name. Aristotle talked about seeing ships obstructed bottom up with increasing distance, right? Okay. And he, from that, hypothesized that the Earth is spherical, or he used that as one of the pieces of knowledge about the shape of the Earth. The distance from where he is to when that ship was obstructed, you didn't know. So nobody was doing any math to say, well, he was this far away, therefore this much of it should be obstructed. It was just a qualitative observation. It got obstructed bottom up. What could cause that? Well, if the surface of the water was curved, that's one thing that would cause it.
Yeah, and then nowadays we see that is not the case because you can use a pair of binoculars or a good camera to bring back the boat.
Well,
Yeah.
no.
So now we know that is not the case.
Aristotle. No, hold on. Let me be clear. Aristotle didn't see. That's not the case. Never, never, never has something gone over the edge, been obstructed bottom up, and then binoculars brought it back. What happened is every single time that any flat earther has been like, look, it went over the curve. It didn't go over the curve. It just got too small to see.
Yeah.
When it's too small to see, it's not over the curve. It's just too small to see. So
Yeah,
do it with
that-
something big. Do it with a big ship or a tall building. It never goes over the curve and then gets brought back by more zoom. Zoom doesn't change the amount of obstruction. It's always the same no matter how much zoom.
Actually, it did. Actually, it did. There are a lot of video footage on the internet where, like you said, a building which is obstructed, and then people use powerful zoom to bring the whole building back. So
No, Fung,
that's the thing. That's the thing.
Fung. I've been 3 years I've been on YouTube, and at least a year before that I was on forums. Never once has any video been shown where something was obstructed more as it went away, and then completely obstructed, and then zoom undid the obstruction. That's never happened. And if I ask you for a video, you won't get one. And we can't take the time right now because you'll be hunting for it for a couple hours. So here's the challenge then to you, Fung. Can you find a video where the amount of something's obstruction changes based on zoom? Right? So you zoom in, there's a certain amount obstructed. So if it's a building, the bottom number of floors, and then you increase the zoom and less of the floors are obstructed. That is the challenge for you. And I've never seen it.
Okay.
So
yeah.
But now Aristotle seeing things obstructed bottom up isn't the only way. We can see that the elevation of the North Celestial Pole changes based on your latitude. Your latitude. Yep. And it's linear. There's only one shape that works with. And I know you said you didn't do much geometry, so I don't know if that will be intuitive to you or not. It is to me. That geometry is not very complicated. There's no geometry that works for the angular elevation of Polaris on a flat surface. It never works. So that's another piece of evidence that the ancients looked at to say, well, it looks like we're on the surface of a sphere. Right?
Yeah. I think we can call it a day here.
Okay.
Because there are several points you brought up that is.
I think
we can. And I have to say that again. You are way better than Quick in explaining things. Yeah. For Quick, I just
gotcha, Craig.
non-stop shouting at each other. It was very. Yeah,
it did. It was a hard one to listen to, I gotta say. All right, let's see. Nimrod said, insert funny joke about Flurf here. Oh, this is an interesting one. Parabindu says sphere distances: Arctic Circle 16,000 kilometers, Tropic of Cancer 37,000 kilometers, Equator 40,000 kilometers, Tropic of Capricorn back down to 37,000 kilometers, and the Antarctic Circle 16,000 kilometers. Those are measured. You can there's ways from home to measure those things. So, and they're accurate. Let's see. Stuck in the YouTube matrix he was on here. He wanted to come in. So NANA for $20 is MC Toon. You need a shot. I do. Ooh. All right. Actually, just a second. You know, my kid gave me this. Gotta show you. For Father's Day, this is a little bit of stuff in there. You see that? What do you think? Inside's a little ship. NA gave me a little bit for a shot, so I'll do it. There we go. There you go, NA, thank you. My grandpa loved that stuff. Sean Hawkins says, you may as well argue that houses are flat, just as silly. Some roofs are flat. Rodent No Last Name says, how can you use GPS data as GPS is orbital satellite data? How can you use satellite data when orbits can't work on flat Earth? Now, when you drive around, do you use a GPS sometimes?
Yes, I do. And
It's tough.
And well, GPS is well. There are ways to pinpoint your location, but whether or not it is coming from outer space, that's questionable.
Well, the thing about GPS is that it is a ooh, I gotta update something from Danny Faulkner just sent me. It's an open standard. You can build your own antenna. You can write your own software to read the data that's coming in from wherever it's being sent, and you get the location. So GPS sends out the location and the time of each satellite, and then you use that distance to trilaterate your position. It's not triangulation.
Yes. I know this part.
And it's all open. The publication is open. There's nothing magic about it. You can write your own GPS from scratch with no help from anybody else, just reading the documentation. And you can even put a directional satellite on it so that you can see where the direction of the satellite is coming from, where the signal is coming from.
Okay.
So Tommy Gronwald says Fung will look it up, but where? I'll send it to you. Rodent No Last Name says, I love how you let them dig their own hole. And Fung, I appreciate your response to it. Batman says, Fung, did you only come here to this debate with the Black Swan as evidence? Yes. That was our agreement, right?
Yes.
Yeah. That was the plan. Earth is Life says, this guy should really have a conversation with Bev. Maybe that's our surveyor friend. Alyssum says, Fung, this guy was an expert. People like QE and Nathan are not experts. They are scammers. Don't fall for their BS.
Okay. So do you mind if I bring up your arguments to them because like you said, the Black Swan argument is first originated by Quantum Eraser.
Yeah.
And I got that argument from him.
Yeah.
So
let me if I could give you advice to what to do.
Okay.
Read the actual stuff that Andrew Young wrote. Come to understand what he talked about. Read some of the citations to the other things that he's talking about. I have a lot of different things on my website from similar places talking about how refraction works, how spherical excess works. I wouldn't go to them because you know what they're going to do? They're going to give you the script. They don't want you to learn. Fung. The last thing that Nathan Oakley and Quantum Eraser want you to do is learn the right answer. They're going to give you their answer because they are not experts. They're just going to give you their answer. If you've watched the stuff on sextants, it's completely wrong. And the people that watch Nathan Oakley's stuff on sextants don't go and actually look up how sextants are actually used. They just take what Nathan says and that's it. Right?
Actually, sextant is presented by another guy. I forgot the name.
Tenth man.
Yeah.
Right?
Yeah. So
No, tenth man isn't a navigator. He hasn't spent decades of his life on the ocean using a sextant to get his position. He doesn't know firsthand about it. He's not an expert. And when I've watched some of the videos, when they go over the sextant information, none of it is based on how you actually use a sextant. This is the key. He doesn't give you the information that would be necessary to get your position on the surface of the earth using a sextant, because he doesn't know how to do it. So go and look up how to use a sextant. See if you can go get a sextant yourself to try using it using the prescribed method, because they don't give you that. They don't give you the method in their videos.
you know what? This is exactly what I'm going to do. Actually, I'm planning on buying a sextant online and then try it myself.
I've thought about doing that too. I know there's a few people that have them.
Shouldn't be too hard, right? You can buy a sextant.
I think they're kind of expensive, but
How much were we talking about in
I
US
don't know.
dollars?
Let's look here. Let's
$1,000?
probably not 1,000. I hope not. eBay. Let's see what they have. Marine sextant for sale on eBay. $500. Here's one for $48. With 2 bids. It's not a buy it now. So yeah, they look like maybe 500 for some of them. Ouch, that's expensive. And here's one. $189 plus $70 shipping.
That sounds about right.
Yeah, you're still around $250. So but I can, if you want, I can send you a couple different step-by-step instructions on how to use a sextant, and it goes over the math.
Yeah. Sure. This is what I'm going to do, regardless.
Awesome. All right. Rodent no last name is S. This is a good question. Maybe you want to think about this. What works on a flat Earth but does not work on a globe?
What works on the flat Earth and does not work on a globe Earth?
Yeah, just something to think about. Put in your head. What is the thing? Because a lot of the time, instead of like, here's why the Earth is flat and give reasons for flat Earth, people are like, let me just go and try to discredit the globe without really knowing, without presenting the flat Earth reasoning, the flat Earth evidence for it. And for some reason that's like, well, if I can poke a hole in the globe, then the only thing left is that the Earth must be flat. That's that's a false dichotomy though.
Well, for now, I would say a sextant. But like you said, you're going to send me some more information about it.
Yeah.
But for now, I would say a sextant only works on a flat plane because it is used for a angle measurement, and you have to have a flat baseline to do so. So
that's what 10th man says. But there is no problem. There is no problem with the sextant because that's not how it's being used. But I'll show you that. I'll send that to you.
Okay. So that's wrong. You're saying that's wrong.
Yeah, his understanding of it is not quite correct. So Wizard of Oz says, if you see someone standing on the horizon and they look back at you standing on the horizon, who is really standing on the horizon? Deep thoughts. Sun Express says, legendary Chinese explorer Zhang He. Yeah, knew the Earth is a sphere.
I don't know who is that. Zhang He.
Yeah, ZHENG space HE. I don't know. That'd be good to look up. I don't know anything
Oh,
about him.
I think I know who that is.
Did I pronounce it correctly?
郑和.
Ah, Zhenghe. There you go.
Did he? Yeah, okay.
C-Force's Marcus Dresden's 100 shill points will forever be mine. There you go. There's some spat between C4 and Marcus Dresden. Draco Farce's Minnesota Classic, drinking out of the glass jars. Doesn't everybody do that? Do you do this in Hong Kong?
Yeah, I do.
Here we go.
Doesn't matter. It works perfectly fine as a mark.
I did not have much dinner. Wow. Holy cow. That was quick. Jeez. The Sun Express says flirts accept latitude and longitude line coordinates. These line coordinates constitute two separate sets of circles. Two circles intersecting at 90 degrees describe one specific shape, a sphere. I will give one thing, though. If the Earth is flat, then latitude, longitude are parts of a polar coordinate system. And if the Earth is a sphere, then latitude, longitude are two of three parts of a spherical coordinate system. There's just a whole bunch of other things that won't work, but if it was flat. And Vindy for 20 Nokias says, you know what? Says, I think Vindy thinks that Fung is that you are. I think you're on the right course. How about that, Fung? On the right track.
Yeah, like I said, I will look into it because I wasn't born a flat earther, right? So
Yeah.
So what you have presented to me today is I would say it's very worth investigating, especially this sphere SS. That part.
And you know what? I will send you right now my website to that. It's mctoon.net/SE, and I do all the math in there and the links to the spreadsheet. So Lael says, on a flat plane, if I'm right under the Polaris and measured it a 90 degrees, how far to move away for that angle to be measured at 89 degrees?
That's 69 miles, right?
Correct. The problem is, of course, 69 miles for each line of latitude, if the Earth is flat, would give a significantly larger equator.
Yeah, the problem with that is the way they determine the angle is by actual observation. Well, in actual observation, the further you go, the things you're looking at seem to drop.
Yep.
To the horizon due to perspective.
Absolutely. Yep.
So it doesn't necessarily be a sphere to obtain this phenomena, because on your model everything is plotted out in a orthographic view where the angular height of the Polaris never change. But in reality, as you go further away, the angular height of the Polaris actually drops. So
yep. Well, let me show you how that works quick, and then we'll wrap it up. How about that?
Yeah, sure.
All right. So here is I'm going to draw flat Earth first, right? There's flat Earth. So we have straight up. We have right there. I'll put it over on the side here, right? 90 degrees right there. Kind of estimating this one, actually. There you go. So right here, we have Polaris.
Yes.
Right? And this is 90 degrees north. That's the North Pole. I live in Minnesota. And in Minnesota, it's 45 degrees north. So I can measure, let me get this one right here. How high is this? I should have put here. I'll put it right at 4 inches right there. Okay, let's put Polaris right here. 4 inches, right? And I'm at 90 degrees, or sorry, 45 degrees. So it's the same. We're going to make a right triangle right here to get my elevation. Now, how far am I from the North Pole if I'm 45 degrees north?
So
Right? How far? What's this distance right here?
I don't know.
Well, you went over it before. 69 degrees per, right?
Yeah, yes, per degree, yes.
And it's
So
40.
you
It's
times-
45 degrees. So 45, 69 times. It's approximate. It's not quite, but we're close. 3105. Right? Now this is a 45, 90, 45 triangle, meaning that this is also 3105. Right? Now this is upside down for you, I know, but right?
Okay.
So that there's now if I go to 30 degrees, right? Or if I go all the way, actually, if I'm halfway, if I go all the way to the equator, right? I can measure the angle for flat Earth, what it should be, right? Now I'll make sure that this distance is correct. I didn't do that.
Yeah, that's my point. That's my point. If you're doing it on an orthographic view, the effect of perspective cannot be shown. Yeah,
Well,
that's
actually,
exactly my point.
orthographic view tells us how perspective happens. That's what we're doing. We're applying perspective. That's what orthographic view gives us. So here we go. This is the angle that we should see. So based on where I am in Minnesota, the North Star must be 3105 miles high. Now we could just measure this right here. If the Earth is flat, then the equator must see this angle right here, which is, I'm getting about 28 degrees. Right there. That's what the flat Earth says that we should have for the elevation of Polaris, the angular elevation of Polaris. I just applied perspective is what I did. It's approximate, might be a degree off.
This one I'm not so sure. This one I'm not so sure because drawing it on paper and versus actual.
I mean, we
versus
can
actual
do the
observation is
we can
very
do the,
different.
well
Because
observation.
what you see in your everyday life, it doesn't have to go very far for the things in front of you to converge into the finishing point, right? It doesn't have to go very far. In the same can apply to
but in your regular everyday life, you're not looking at something that's measures to be 3,000 miles high.
So that's why I say I'm not so sure about this method of determining angles on the flat Earth.
Well, then what's the right method? This is just applied geometry.
You have to also consider the size diminishing from your point of view because everything tends to be smaller
And it did, yeah. And so this, as you get farther away, this gets smaller too. Its angular size gets smaller. So when you're here, the angular size of this distance is 45 degrees. And as you get farther away, this angular size is only 28 degrees. It's smaller. somebody did the math here, says 26.57 is the from trig, right? So I wasn't super particular on that. So like I said, I was a bit less than 1.5 degrees off. So not too bad for kind of a sloppy measurement that I did here. But if there's a different way to do the geometry, then I'd love to see the different way to do it. But I've seen flat earthers say that it needs to be done differently, but never been presented the correct way. Right now, and you've said before that math isn't your thing.
Yeah.
Right? So are you going to come up with a different math? No, I don't think you're going to.
Of course not.
Yeah.
Especially not now.
Yeah.
Yes. So this is something we should think about.
Yep.
All
right. Let
in
me.
the back of my head, I think there's something wrong with it.
Well,
And
show me what's wrong with it, and I'd love to see how to do it the right way then. But that is how you do perspective. You can do it. You can test it for yourself in a long hallway. You can measure a close angle. You can go farther and predict the difference in height in angular size. So,
Okay.
Lael says, "What is the altitude of Polaris on flat Earth?" Well, I just did it. It's gotta be from Minnesota through 3,105 miles. The problem is it's different everywhere you measure it. So, String News 1 says, "Lael, there is no flat Earth, only Sergeant Schultz Earth. I know nothing. Nothing." Are you a big fan of Hogan's Heroes?
No.
Have you ever heard of Hogan's Heroes?
No.
Nope.
Never heard of it.
Sergeant Schultz, look him up. Wiggles for 5 Canadian says, "Fung, I have a $500 challenge for this zoom to restore effect on bottom-up obstructed objects across the ocean. No submission for flurfs. Why?" Well, Fung, there you go. Wiggles will pay you $500 if you can zoom to restore something bottom-up that's been bottom-up obstructed. If you've seen it a lot of times, that should be a quick $500.
Okay.
And Stringer News 1 says, "If the Rayleigh criterion makes objects disappear bottom up at the horizon, why doesn't the same thing happen to Polaris?"
Sorry, I didn't catch that.
The Rayleigh criterion is one of many different things that some flat earthers have said causes bottom up obstruction. Doesn't quite match.
I've never heard of it. I think something is obstructed in the ocean is probably due to waves. Yeah.
Waves. Okay. All right. Well, Fung, thank you very much. People, if you want to send anything to me to send to Fung, I will route it to him. Any of the things that we were talking about, particularly if anybody has a sextant experience and has a manual or book that you like, a process you like, I think that would be a very useful thing. So, Fung, anything you want to say as we wrap it up?
Well, thank you very much. It's been a very fun time with you, and a lot of new points that I will definitely look into it. And yeah, thanks again.
All right, Fung, thanks a lot.
Yeah.
I'm going to talk with people a little bit here, so you can stick around, or you can close the call.
Yeah, I think I'll leave. I haven't eaten anything yet. So,
all right.
Yeah, thank you.
All right, thank you.
All right, thank you. Bye.
Man Devil, you just did a Colonel Klink impression instead of a Sergeant Schultz. I did. You're right. Hogan! It's Schultz. I know nothing. My mom loved that show. Oh, that was fun. I will send him to Bob the Science Guy. A little scratchy on the throat now because all right. Did somebody send me the diagram and then I didn't use it? I don't know. Whoa. I'm looking. I'm trying to look. All right, people, you gotta go look at the Discord server. Oh my gosh, I can't. Nope, I gotta stop looking. NA wants to send a lobotomy drill. I think Fung. Let's have hope for Fung. If you see him on Facebook as Globby's Hey, say hi, encourage him. I think if rather than retreating back to Nathan Oakley, if he were to actually go and read up on how to do things the right way, I think it would be very useful for him, and he might find it beneficial. So let's see here. I'm going to do this. So that was fun. Fung listened. I think that might be good. I came out guns blazing. I knew every single one of the QE script, and I didn't need to use this one. Oop. Oh, it's muted. Just a second. I have to unmute. All right, here goes.
I'm claiming that you haven't even actually accounted for all the variables, and you're touting your trigonometry that literally hand waves dismiss one of the most important variables when it comes to perception, which is refraction.
Thank you very much, Austin. I love how Austin destroys the black swan.
Refraction, which we immediately and adamantly claim is always present because there's temperature fluctuation and atmospheric conditions that are consistently affecting what you perceive.
Absolutely. Well, Sun expresses, does Fung know there are Cations in Lake Titicaca? That's funny. I love it. All right. Well, thank you very much, everyone. That was fun. I've been busy. I've had so much going on. I'm not going to do an after show tonight. A lot of the time I would, but I need to get back to some other stuff and get some rest. So thank you very much, everybody. It's been super fun. I will try to get him back, and I will try to get Fung some good information so that he can maybe think through things a little better and come up with better answers then. So I said locations. Locations. That's right. Oh, I loved that last week. That was so funny. Trey Hutchinson, he put his foot in his mouth and just kept chewing it. Chewing. Don't forget on Saturday, it's unless something changes, I'm debating Alex Stein on Modern Day Debate about the moon landing. That should be interesting. I will probably do an after show for that one. So anyway, thanks a lot, everybody. I will definitely, I don't know what I was going to say. I'll see you all later. Thanks a lot. Bye.